Hi, in this video, we will learn how to solve the homogeneous part for the second order ODE in order to find the complementary solution. In this example, we have second order ODE where the A, B, C are given in constant. So the right hand side here is equal to 0. Therefore, we know that this is homogeneous ODE. So if you have homogeneous ODE with constant A, B, C like this equation, then we can use the following strategy to solve the problem. So in this case, we want to find y with respect to x. So we can assume the solution should be in the exponential form, where the m is equal to unknown. And the m can be found from the characteristic equation. For example, in this case, a, b, c are given equal to 1, -4, and 3. So to solve this problem, first of all, we know this is homogeneous linear ODE, therefore the solution will be in this format. So please remember, the solution for the homogeneous ODE will be in the exponential format. So to verify this solution, so you can differentiate it twice like this and substitute inside the formula. Then you can substitute the y prime, and y double prime inside this equation. So your y should be equal to exponential mx, y prime is equal to me mx. Lastly, your y double prime is m squared exponential mx. Then you can extract the exponential mx outside like this. Multiply with m squared minus 4m plus 3. Since we know that the exponential mx cannot be equal to 0, right? So to make the equation equal to 0, then we need to let m squared minus 4m plus 3 equal to 0. So this is the characteristic equation where we can find the m from here. From the characteristic equation, you can solve the quadratic equation here to find the m. Basically, you will have three cases where the m can be either real number, complex number, and lastly, repeated root. Since the characteristic equation here is a quadratic equation where we can use this formula to find the root. So if you solve it, you should be able to obtain two distinct roots, and these two roots is equal to 1 and 3, and they are real numbers. Instead of using this formula, you can also consider to use calculator to find the root. So these two approaches are acceptable. With that, we can continue to substitute the m1 and m2 inside the solution here in order to obtain y1 and y2, where the m1 is equal to 1 in this case, m2 is equal to 3 in this case. In this case, y1 and y2 are linearly independent solutions. Therefore, we can use the superposition principle to combine the solution for the y1 and solution for y2 in this linear combination. So in this case, you should know the a and b here are the arbitrary constants. So if you don't like the a and b coefficient, you can also use other coefficients to represent the constant. With that, we success to solve the homogeneous equation here, and the solution is equal to the complementary solution. In simple, to solve a homogeneous ODE where the right hand side is equal to 0, then you must know the solution is in the exponential format. So to find the unknown m here, which is the root, you need to know how to form the characteristic equation. So instead of go through this long derivation, you can directly form it from the equation here, where you see the y double prime will directly change to m squared, y prime will change to m, and y will just change to 1. So directly you can obtain the characteristic equation from here. In this case, you success to obtain two different roots where both of them are real number. So you can substitute m1 and m2 inside to obtain your first and second solution, and later you can use the superposition principle to combine them. So this gives you the final complementary solution. And this is the solution for the first case. In this example, your A, B, C are equal to 1, 4, and 17 divided by 4. We are going to find the y with respect to x in this case. Since this is homogeneous ODE, we know that the solution is in the exponential format here. And we need to find the root for the m. So we can find it from the characteristic equation, where you can form it by let the y double prime equal to m squared, y prime equal to m, and y here become 1. So 1 multiplied this, we should obtain 17 divided by 4. So we can continue to solve this by using the formula here, or using calculator. Then in this case, you obtain two complex numbers. So you can substitute the m1 inside the exponential formula to obtain the first solution. Then you continue to substitute the m2 inside here to obtain the second solution. And these two solutions are linearly independent. Therefore, you can obtain the complementary solution equal to the linear combination of the constant multiplied with your first solution y1 plus the second constant multiplied with your y2. So this is the final answer. So in this case, you have a pair of complex conjugate roots. In general, the complex number is given by a plus bi. So the complex conjugate for this complex number is equal to a minus bi. Where you see that for the first root, m1 is equal to negative 2 plus 1 over 2i. So this is your m1. And for your m2 here is equal to the complex conjugate for the first root, which is negative 2 minus 1 over 2i. Right? In simple, for the case 2, you have complex root. So in this case, you still obtain two linearly independent solutions, y1 and y2. Therefore, you can still use the superposition principle in order to combine the solution to obtain the complementary solution. So you can see that the strategy to solve the complementary solution is similar for case 1 and case 2, where the root m1 is not the same with m2. Let's continue with this example. So you have a equal to 1, b equal to negative 4, and c equal to 4. So this is homogeneous ODE where the right side is equal to 0. So you want to solve this equation to obtain the dependent variable, which is y, with respect to the x. So for this type of homogeneous ODE, you know that the solution is in terms of the exponential format. So you need to solve for the m root here. So you must continue to form the characteristic equation where you let the y double prime equal to m squared, y prime equal to m, and y equal to 1. 1 multiplied 4 still give you 4. So from here, you can use formula or using calculator to solve this, where you should obtain your m1 and m2 are equal, which is equal to 2 here. This is known as repeated root, where the roots are the same. So you can continue to substitute m1 equal to 2, m2 equal to 2 inside the solution. So you obtain y1 and y2 here. But if you look at the solution, both of them are the same. Therefore, we can say that this is linearly dependent solution. We know that linearly dependent solution here is not good, because instead of having two solutions, you only have one solution out of these two, because these two solutions are the same and they are linearly dependent. So how can we find another missing solution? Where you should know, when we solve the second order homogeneous ODE, you should obtain two solutions. So now from here you only have one solution, and where is another missing solution? To find the missing solution, you need to perform a treatment. So your second solution, you need to multiply with x, which is the independent variable. where you can find from the ODE equation here. So y is your dependent variable, and then your x here is the independent variable. So therefore, we need to do the treatment by multiply with the independent variable, which is the x. So x multiply the y2 here, so give you x exponential 2x. So these two solutions are linearly independent now. Therefore, your complementary solution is equal to constant a multiplied with your y1 plus constant b multiplied with your y after treatment. So without treatment, you have exponential 2x and exponential 2x here. So since these two are linearly dependent, therefore a and b here can be combined, which gives you one solution only, which is incorrect. In this example, you learn how to perform the treatment by multiplying it with the x. So by doing this, you have two independent variables. Therefore, this is the final complementary solution. You need to be careful if the independent variable is changed to other, for example, is dt in this case. So from here, you are going to find the y with respect to t. So the solution for the homogeneous ODE, you know it will be in the exponential format. So the independent variable is t, therefore you need to change the x to t in this case. After you solve the characteristic equation, you shall obtain repeated root. So your y1 and y2 here must be in t variable also. So when you compare y1 and y2, they are the same and linearly dependent. So this is not what we want. Therefore, we need to perform the treatment to obtain linearly independent solution. So we need to multiply it with the independent variable, which is t in this case. So you need to replace all the variables to t. With that, you obtain the first solution to be exponential 2t, and your second solution to be t multiplied with exponential 2t. So you can combine it by using the superposition principle, where you multiply a with the y1 plus b with the y2 after the treatment. So the x here, you need to be careful, you need to replace with the t. Right? So this is the final answer for the complementary solution, when you change the independent variable x to the t. So far, you have learned that we need to consider three cases, case 1, case 2, and case 3 here, in order to solve the homogeneous ODE. So if you have real and distinct roots for the m1, m2, or if you have a pair of complex conjugate roots for the m1, m2 here, then the complementary solution can be written in this format. So no treatment is needed in this case, where you can see all the solution y1 and y2 here. So this is your y1 and this is your y2. So they are in the exponential format. You need to be careful in the third case, where you have repeated root. Previously, we do not need treatment because the m1 and m2, they are not the same. Therefore, these two solutions y1, y2, they are linearly independent. However, in this case, m1 is equal to m2 here. So to avoid linearly dependent solution, we need to multiply the second solution here with the independent variable. By doing this, so you obtain a new y2. So this is after treatment. Therefore, you can see the complementary solution for the third case here is in these two formats. So you have the exponential as well as the s exponential format. So don't forget the treatment if your root m1 is equal to m2. We can use the b squared minus 4ac as the indicator for these three cases. For example, if you compute from here, b squared minus 4ac, if this value is greater than 0, then m1 and m2 are the real and distinct roots. So if you obtain b squared minus 4ac less than 0, so it will be second case where you have a pair of compressed conjugate roots. Lastly, if it is equal to 0, then you will obtain the third case where you have repeated real roots. So if you solve the homogeneous ODE and obtain the root to be 4 and negative 5 here, so the complementary solution will be equal to this format, where you just substitute m1 equal to 4, m2 equal to negative 5. So if you obtain complex root, for example m1 equal to 5 plus 3i, and your m2 is equal to 5 minus 3i. So in this case, your complementary solution will be still using the same format. So you just replace the m1 equal to 5 plus 3i inside, and your m2 here, you just substitute the 5 minus 3i inside. So this is your solution. Lastly, if you obtain repeated root, for example m1 and m2 are the same, which is equal to 3. So in this case, you can substitute the m1, m2 equal to 3 inside, and don't forget to apply the treatment. For the second case, where you obtain the complex root, m1 equal to 5 plus 3i and m2 equal to 5 minus 3i, so you can write the solution in this format, and the exponential 5x you can extract out, and in the bracket you have the imaginary component. You can further reduce this to the cos and sine format. So this is another alternative where we represent the solution in the second case. So your m is equal to 5 in this case. So you can substitute. A and B are constants. So the beta here is the imaginary number, which is equal to 3. So you can substitute the beta equal to 3 inside this equation to obtain this answer. By doing this, you success to convert the exponential format for your complementary solution to the trigonometric format. So both of these formats are acceptable. You can check the appendix 12.1 to find the conversion from the exponential format to the trigonometric format. This can be done by using the Euler formula, where the exponential I multiplied with x give you the cos x plus I sin x. And if the x here is negative, where you have negative x, so this is equal to cos negative x plus I sin negative x. Since we know cos negative x is equal to cos x, and sin negative x is equal to negative sin x, therefore we can obtain these two equations. For the complex root case, for example, the root 1 is equal to 5 plus 3i, the root 2 is equal to 5 minus 3i. So the complementary solution can be equal to this format, where you substitute the m1 and m2 inside. So we can extract the exponential 5x outside, then you obtain this exponential format. So you can see that the exponential 3ix can be converted to the trigonometric format using the Euler formula. So in this case, if let's say your exponential I multiplied with 3x, then the x inside here will be changed to 3x also. With that, you obtain this. So for this term, you have exponential negative 3ix. So using this formula, if you have negative 3ix, then the cos x inside here and sin x inside here will change to 3x. With that, you can convert this to this format. Then you continue to collect the term for the cos 3x, where you have c1 plus c2 here. After that, you collect the term for the sin 3x, where you have c1 multiplied with I and c2 multiplied with negative I, which gives you negative c2i. Let the a equal to c1 plus c2, then we can replace this term with a. Let the b equal to I multiplied with c1 minus c2, then we can replace this equal to b. With that, we success to convert from the initial exponential format into the trigonometric format here. So the derivation here is just for your understanding. You don't need to memorize the derivation. The most important thing is you know how to convert from the exponential format to the trigonometric format. So you see the exponential 3ix and the exponential negative 3ix can be converted to the cos and sine format here. You need to be careful. The angle inside here is without the I. It has only the 3x, which is obtained from here. So far, we have success to use the exponential solution as well as the characteristic equation to solve the homogeneous ODE with the constant A, B, C coefficient here. In this case, we have homogeneous linear ODE since the right hand side is equal to 0. But in this case, the coefficient here is no longer constant. It is s squared, ax, and b. So this is known as the Euler-Cauchy differential equation. So all of the coefficient here is in the function of x, which is the independent variable. Therefore, this is still linear ODE. The strategy to solve this type of equation is we let the x here equal to exponential t. And by doing this, we can convert it to the previous format and then solve it using the previous strategy. So previously, when you have constant coefficient ABC, you can find the solution in this format, or if you need treatment, we need to multiply with the independent variable. So in this case, the coefficients are non-constant. So to convert the non-constant into constant coefficient, we can use this substitution. So the following information is for your extra knowledge. First of all, let's convert the x multiplied with dy over dx to constant coefficient. We assume the x equal to exponential t, and from here you convert the exponential to the left hand side, you obtain ln x. Therefore, t is equal to ln x. So you continue to differentiate both sides with x, then you obtain dt over dx equal to 1 over x. From the chain rule, we know dy divided by dx is equal to dy divided by dt multiplied with dt divided by dx. So we can substitute this inside to obtain this. Then you can multiply both sides with x. So this will be cancelled to obtain dy over dt. And on the left hand side you have x dy over dx. So this is the first equation. We can continue to convert this term to a constant coefficient. So this is the step. We can proceed from here, and then you differentiate both sides with respect to the x. So on the left hand side, you constant the x and differentiate the dy over dx, give you y double prime, and you constant the dy over dx and differentiate x, you obtain 1. On the right hand side, remain. From the chain rule, we can expand this term into this, where if you cancel the dt here, you still obtain the same term. So you have success to find the dt over dx equal to 1 over x previously. With that, you can substitute inside this equation to obtain this. Then the differentiation here can be further simplified into y double prime. From here, we success to use the chain rule to obtain this result. Therefore, we can put the left hand side here and the right hand side is this. So we can multiply both sides with x to cancel this term, and on your left hand side you obtain x squared and x here, which is this. From the equation 1 here, let's substitute x dy over dx equal to dy over dt. So this can be equal to dy over dt. And when we bring this to the right hand side, it becomes negative, which is this term. So this is the second formula. In this example, we have homogeneous linear differential equation with non-constant coefficient x squared and in x here. To solve this type of problem, we need to substitute x equal to exponential t. By doing this, we can obtain two important formulas here. By using the first formula, we can convert the x dy over dx into dy over dt. By using the second formula, we can convert the x squared d squared y over dx squared into d squared y over dt squared minus with dy over dt. Then you can continue multiply 2 inside. So this one gives you this term. Here you obtain negative 2 minus with 3 you obtain negative 5 dy over dt. Lastly, you have negative 3y. So you have success to obtain constant coefficient by using the formula here. From here, we want to find the y with respect to t. So we know that for this type of problem, we can assume the solution in the exponential format. Let's form the characteristic equation. So we replace the y double prime into m squared, y prime into m, and y into 1. Therefore, you obtain this characteristic equation. So you can use the calculator to compute the root. The first root is equal to negative 0.5, second root is equal to 3. So we say this is real and distinct root case. Substitute the root inside the solution, you obtain your y1 equal to exponential negative 0.5t, and your y2 is equal to exponential 3t. Since both of the solutions are linearly independent, therefore we can combine them using this linear combination. So you obtain your complementary solution equal to c1 multiplied with y1 plus c2 multiplied with y2. You see the solution that you obtain here is y in terms of t, but the original problem here, we are going to find the y with respect to x. So you need to convert the t into the x function. This can be done by using the substitution that we used previously, where the x is equal to exponential t. So we can substitute the t equal to ln x inside the equation. For example here, exponential negative 0.5t, substitute the t inside, you should obtain exponential negative 0.5 multiplied with ln x. So this can be converted to exponential ln x power of negative 0.5. So exponential and ln here can be cancelled to give you x to the power of negative 0.5. With that, you obtain this solution. So over here you have exponential 3t. So this can be changed to 3. This changed to 3. And then here you have x power of 3, where the exponential and ln can be cancelled. Therefore, you obtain x power of 3. So this is the final solution.